Good evening, guys. Hi, guys. Okay, so let's just give it one more minute so that we actually have mostly everybody joining and we can start. Okay, let's get started so we don't run out of time. Hi, guys, how are you? Okay, let me see. So we can admit people here and there. So we have 12 people. We might as well start. Let's see. Okay, so the last time we were talking about the phase shift algorithm, right? We're starting to talk about, in general, pulse wave Doppler. Right, and some of the limitations and things to keep in mind in practice. And we were going to make it to Kasai's algorithm. This is probably the first algorithm in the literature that allowed creating color flow images. And from a historical perspective, it's very important for us. There are other algorithms, that were released afterwards that, probably do this in a somewhat more elegant fashion, like accounting for several limitations like a size algorithm may have. But for the purposes of this class, I think this is probably sufficient for you guys to know, right? Then you can read the literature and learn more about, other more advanced topics that we're not going to address in here. Kasai's algorithm is actually one that is based on calculating the autocorrelation of an ensemble of data in a slow time domain. Okay. Remember last time we said we have fast time and we have the slow time, right? And the slow time is the one that corresponds to different firings of the ultrasound transducer, which happens, at the rate of kilohertz, rather than the sampling of the RF data, which happens at a rate of, megahertz, right? And that we call the fast time. So we're talking about the autocorrelation in the slow time. And if you remember the last time we said we have, different pulses that are being fired, right, at different instance in time. So if we draw a line, that's cutting those RF lines across, the vertical direction. So for us, it would be at a fixed time after each firing. Then we were going to have a profile. And we said, okay, so how do we actually calculate the flow speed based on the analysis of that profile? And we said that in general, it was really, really hard to look at it and probably say something meaningful. We knew that, if there was no flow, that profile was going to be a constant. But if there was a flow, then things were meant to be changing, right? That's what we said the last time. So in general, we can calculate the autocorrelation of the signal as a function of tau, right? Our received signal as a function of tau for a given instant of time, right? And that autocorrelation can be calculated, like in general, right, at different amounts of lag, right? So you remember the autocorrelation, and the definition is actually given in there, right? The autocorrelation of the signal, right, RT, is given by, in this case, it would be the integral, because we're assuming, like for mathematical purposes, usually we start the description with a continuous time counterparts, and then we go to discrete ones, right? So the autocorrelation would be the integral with respect to tau, because that's the direction that we're actually correlating things at, of the signal in tau times the signal in tau plus t, where t would be our TPRF, right? So it's like one firing, shifting it one firing, right? Like when this becomes a discrete counterpart, right, it actually means that we have the signal that's composed of the slow time profiles, and then we grab that signal, we shift it in one sample, right, and we calculate the autocorrelation. Kasai's algorithm, like the people that developed it, which, as you would imagine, the first author was, his last name was Kasai, right? I mean, he's a fellow from Japan. The flow velocity can be estimated as minus c divided by 4 pi f naught TPRF multiplied by the arctangent of the imaginary part of that autocorrelation divided by the real part of the autocorrelation. How do you actually come to that expression? That's something that's beyond, the spirit again of the course, to go into the depths of the definition of the derivation of that. But you can actually go to the paper and read it if you want to, and I can actually upload the paper to the PyDaya site for the course in case you want to read the paper. Now, in practice, right, what we're going to use is signals that are sampled, of course. So this autocorrelation, right, the imaginary and the real part of the autocorrelation, we are going to estimate it by using discrete counterparts, right? So instead of having an integral, we are going to have a summation, right? Because the autocorrelation would be a discrete autocorrelation. So in this case, it would be, first on the numerator, and sorry for going back and forth, but in the numerator, you have the real part, the denominator, sorry, the imaginary part in the denominator, you have the real part, right? And you can actually start to calculate what would that be, right? Because again, you have the imaginary part of, in this case, it would be S would be X plus I times Y, right? And the same thing for S in tau plus T, which actually becomes, like M plus 1 if you want to, right? If we're using, or I, in this case, I plus 1, right? So you can actually, like, very easily, right, set up that product, and you can keep the real part and you can keep the imaginary part, right? And this would be the real and the imaginary parts, and that's it, right? It's actually relatively straightforward to do it from the definition. I'm pretty sure you guys can do it in 5 minutes. So this is what you have. And if you actually look at it, right, when you have NC equals to 2, right, so you're using 2 pulses, right? NC is the number of pulses that you're using. Then that leaves you with, the summation becomes just one number, because it's going from 0 to 0, right? So the Kasai algorithm and the phase derivative algorithm become identical, which is kind of neat. And actually, you can just go to this, right? And this is the expression that you have over there, right? The 4 pi, the 4 pi V divided by C times F naught times TPRF equals to arctangent of this. So that's exactly the same thing that you end up having in here. Okay, so they're both the same, and that's kind of neat. That's good that it's the case, right? Because they have self-consistency, right? Which, remember, I always tell you, it's good to check for limiting cases, right? I mean, if things actually do something meaningful along the lines of what you are thinking it should do. So when you really think about it, right? what is Kasai's algorithm doing? Kasai's algorithm, like in general, it would use more than two transmissions again, right? So in essence, what it's doing is it's calculating some sort of an average, right? When calculating the arctangent of blah, right? Instead of calculating like real and imaginary parts just once, and just dividing them and something happens, what it's doing is it's just calculating an average, right? I mean, I'm going to calculate an average of what the imaginary part should be, and I'm calculating an average of what the real part should be. So I'm not transmitting once and then twice and that's it, but I'm transmitting a third time. So I'm going to process, the first with the second transmission, then the second with the third, then the third with the fourth with the fifth, right? And in each one of those, I'm going to be looking at, this real and this imaginary part of the autocorrelation, which in the end, they're going to give me hopefully updated estimates, or better estimates for what this phase shift is going to be equal to. Like if you want to look at it from a very, very simplistic point of view, that's what it's doing. And it's something that probably, fairly reasonably you would think is a straightforward extension of the phase shift algorithm. Straightforward in the sense that, I mean, that's just what it is, right? I mean, as an engineer, rather than taking one measurement, you repeat the measurement several times, right? You average, and hopefully the number that you have is better, than not averaging, because it would be more insensitive to the noise. And that's it. Questions up to this point? So I'm assuming there are no questions. The real advantage of, yes.
So in the end, it was kind of like what we discussed at the end of the last lecture, that we have a mean of all the shifts.
Well, I think actually the last time what we were looking at was this, right? It's a phase shift and you only need two transmissions.
Yeah.
So in here, basically, it's like in a sense, right? I mean, when you look at it from a very, very simplistic point of view, it's doing the same thing, but rather than just using two transmissions, use several, and you compute the same thing, for pairs of these transmits, because these things are calculated in pairs. And then you just average everything out before you calculate what the actual phase shift is, right? Again, from a simplistic point of view. The formalism of how you derive it, I mean, it arises from a completely different place, actually. It can be a fairly, I mean, sometimes I think that it's a derivation that may be confusing to people that do not have relatively advanced topics of signal processing under their sleeves. But, it just comes to an expression that's relatively simple, and I think it ties very nicely with, the other things that we were looking at. Now, the true strength of Kasai's algorithm, however, has to do with, again, the idea that we're using an ensemble, like we're using more than two firings. And again, yes, the simplest way that you think you can exploit that is by doing this average thing that's on the slide. That's the simplest thing that you can think. But there are two things that you can do with Kasai's algorithm that you wouldn't be able to do with a simple phase derivative phase shift algorithm, which is the calculation of turbulence, which is something that we're not going to talk about in here. And the other one is the application of wall filters, which is something that we are going to talk about in here. So roughly speaking, right? And we said that before, we talked about it, right? You have tissues that are stationary, and you have, in our case, it would be the blood that's flowing, and you're going to take measurements of signals coming from blood vessels, and that data is going to have, some noise on top of it. but more than just having some noise on top of it, right? The problem is that there will be echoes that come from the stationary, non-moving, let's emphasize that a lot, right? Let's be redundant. The non-moving components, those are also going to produce some signal that's going to be mixed with the signal from the blood flowing in the vessels, okay? So I'm going to go to the whiteboard for a second. Like imagine in general, right? I mean, you have a transducer in here, right? And again, transducers have radiation patterns, right? So we may have a phantom, like something like this. And of course, in principle, we're not dealing with phantoms, but you're gonna get the point, right? And there may be like a bezel in here, and you want to create a color flow image. And when you're in here, maybe your change colors, and maybe you have, you know, a beam that points in this direction, right? And you're getting signal that's coming from like in between this depth and this depth, right? You have signal that's coming from inside the vessel. And if that would be the way that acoustic transducers would radiate, then we would know that, you know, that would be great. Now, is this the way that transducers radiate? You only have one beam and that's it? So what else do transducers, how is it that real transducers radiate?
Like a gene function.
Right, so you have one main beam, right? A main lobe, but you also have side lobes, right?
Yes.
Most of the energy is coming from the front, but some energy is also coming from the sides. Like if you have a really crappily designed transducer, of course, you may even have grating lobes, but that's the crappiest case, right? That you not only have like some coming from the sides, you have a lot coming from some sides, right? But in general, if it's properly designed, right? And yes, a circular piston, it would be a jink, right? If it's not a circular piston, if it is a rectangular transducer, right? Like an actual array, it would be a sample sink, right? Correct. But the thing is, you are going to have not only this, but also you're going to have, you know, like, and this is horribly drawn, but you kind of get the point. You're also going to have side lobes. So some signal is going to come from the sides also, right? And again, this is horribly drawn, right? But you're gonna get the point. And yes, of course, this is not meant, like this is not drawn to meant that the energy coming from the side lobes is the same energy, right? I mean, it's like you guys were saying, like I have my radiation pattern, and it would probably look something like this, you know, like, and again, it will be symmetric very likely, right? It's going down and it's going down. Maybe this thing over here is like at whatever, right? Like minus maybe 20 to minus 30 decibels or something like that. So clearly most of the thing is going to go from inside the vessel, right? Some energy is going to come from the sides. And it kind of may look like it's not a big deal, you know, like it's like, yeah, it's okay. I mean, 30 decibels is like 3 orders of magnitude, right? It's like, who cares? That's what one would think. But the particular problem with imaging blood flow is that, remember that the signal coming from inside the vessel is like super archi mega weak. Like so weak that in a typical echographic image, it looks pitch black, right? So let's say that, you know, the signal that's coming in, it's at, I don't know, minus 40 decibels, right? And at that point, it actually does matter if you have side lobes, you know, that are at minus 20 dBs or minus 30 dBs. Because all of a sudden, that's actually stronger than the signal that you're trying to analyze. Do you understand that?
But, I mean, why would it be stronger if the main lobe is always like bigger?
Because if the blood is like, if that inclusion over there is scattering at minus 40 decibels relative to the background, right?
Mhm.
But you actually have side lobes that are going to produce echoes going back to your
Yeah.
transducer that come from the background.
Oh,
So
right.
as you can see, this is coming from the background and this is coming from the background,
Mhm.
right? And that is, let's say, minus 30 under, you know, because of the radiation of the transducer, right? The signal that the main lobe is measuring is 40 dBs under, you know, the signal from the background, but you're picking up signal from the background reduced in 30 dBs. So even if it's reduced by 30 dBs and in itself is not that important, it's still above, you know, the signal that's coming from the vessel itself, which is 40 dBs below the signal
Mhm.
coming from the background. You see it?
Yes.
And in principle, it really doesn't have to be, you know, that dramatic. It may be that they're comparable. It may even be that, you know, the signal that's coming from the side lobes and stuff is somewhat reduced. But what you want is for that to actually be like a lot reduced. So it doesn't mess up with your estimates. Again, especially considering that the signal in itself is really weak, you know, so you have a lot of noise and you have a lot of issues, you know, in handling that data. So, you know, just saying. So that is a problem. So let me go back to the slides. That is certainly a problem. But that is a problem that can be very easily reduced by, you know, applying some relatively trivial processing. And actually, let me go back to the whiteboard again. Sorry for jumping back and forth so many times. Imagine that what you have is something like this, right? Let's change colors to black. And do you remember last time we were saying, okay, so like there is some signal, right? Again, horribly drawn, but you kind of get the point. And this would be in T, and then, you know, some signal, and this again would be in T, and this is along the direction of tau, right? So if I were to actually do something like drawing a line through here, you know, and then I have a signal that I'm going to look at as a function of tau, and, you know, again, there would be samples of it, right? Like something, there would be another sample, there would be another sample, there would be another sample. And we said, so what happens if the tissues are stationary? If the tissues are stationary, we said that profile as a function of tau is going to look like a constant. It's going to be a constant, right? Now, if it is a constant, right? Does that mean that if I were to do something really simple, like for example, I'm going to create, and let's call this thing over here, I'm just giving it some whatever name, right? Or we actually call it that this would be an S for a fixed time of tau, right? Or something like that. That's what we said we would have. So what happens then if I have something like S T of tau minus S T of tau minus 1, for example, right? So what am I doing in there? I'm actually saying I'm going to subtract, right? Like I'm going to have this curve, right? That's down there. I'm going to calculate a new one, which is generated by like shifting in one sample and subtracting, right? Or equivalently, I'm going to generate a new one that has at samples like 2 minus 1, 3 minus 2, 4 minus 3, right? What would be the case? If I were to do that, what would that, I don't know, let's call it like difference in tau, right, or something. What would this be equal to if the profile is a constant?
Zero.
Correct. It would be equal to 0, right? And that is actually very interesting because this is telling you that if you were just to grab, you know, that data, you were to calculate this difference signal, then what you are expected to get would be exactly equal to 0 if the signal comes from perfectly stationary tissues. So you found a way to eliminate the signal that's coming from stationary tissues. So in principle, you could argue that if you were to calculate that different signal, then it will perfectly cancel out things that occur for signals that, you know, come from stationary, then the rest of it will come from, you know, things that are moving, and you can analyze that, and hopefully you get something that's only related to the part of the data that's, you know, coming from moving targets. The thing though is, in practice, that would only cancel out things that come from tissues that are not moving at all, right? But it may be, you know, that some things come also from, I don't know, the person is breathing probably, right? So even though you're actually capturing signal really, really fast because the person is breathing, then you're still, you know, going to get something that is moving slightly, you know, again, even if it's stationary tissues, you're breathing, so there's a relative movement that's very, very subtle that is really in there. And that's still going to be a problem, right? So what does this mean? Like in general, right? In general, when you look at this slow time domain signal, right? And this is the empirical thing that we were talking about the other day. If it's completely stationary, it's not moving, the more, you know, the blood is flowing or the more the tissue is moving, the more changes you're going to see in the profile of this S of tau signal. The faster it moves, the more changes you're going to see. So it basically tells you that what you want to preserve is the high frequency information. The low frequency information is actually coming from things that are not moving, right? And because you know that, you know, if it were to come from things that are slowly moving, that would be great. But you know that in practice, those are very slowly moving things actually may come from adjacent tissues rather than from the vessel itself. If you think about it, you know, from a signal processing perspective, this thing that we just did here, calculating this difference signal, it corresponds to, I know it's a subtraction, but it corresponds to an actual operation that's very common in signal processing, and you probably talked about it, you know. What type of operation is that, guys?
A derivative?
Yes, it is. But when you have, your signal, so you have signaling here. So basically you're looking at a signal that's generated as, combinations of samples of another signal. This corresponds to what operation for signal processing? Like imagine that rather than being, this minus this, it would be A times S tau plus, B times S of tau minus 1, right? And in this case, we would be looking at a specific situation where A is equal to 1 and B is equal to minus 1. But what would that be?
A linear combination.
Yes, it is. And we actually call that filtering.
Yeah.
So this is a filter actually, right? And if you look at the specific case of, A equals to 1, B equals to minus 1, that is a high pass filter, right? And we know that. I mean, if we look at the frequency content of the 1 minus 1, we know that it's going to be, 0 at 0, and then it's going to, let everything at, half Nyquist, just completely make it through, right? So what this is telling us is basically that we are applying a high pass filter on the signal S of tau. And again, it follows logic and intuition. The low frequency part, right? The slowly changing components of that signal, we're assuming that it comes from surrounding tissues. And we don't want it in our analysis. So we're filtering them out and we're only keeping the high pass part of it, right? Which is the one that carries information about things that are moving faster. Now, if we only have, two samples, like we only have, two transmissions, so we only have two samples for S, then the most that we can do are things like that, right? I mean, we can say, well, it's going to be the signal in tau minus the signal in tau minus 1. Or, you can maybe not make it 1 and minus 1. You can make those coefficients like, I don't know, 0.9 and minus 0.8 or something. And with that, what you're doing is you're going to be rejecting a little bit more of the low frequencies, but not quite so, and you probably know this from signal processing anyway, but you can actually design very, very nice filters. But if you actually want to develop these more sophisticated filters to more properly eliminate, you want to get rid of, rather than having a filter that has a frequency response that is like this you probably don't want, right? What you want is something more like this. I mean, you want to reject something like up to this point, I cut it off, and then I want it to level out. So that, I mean, this low part of the frequencies is like, I make a clear cut in here. This, I assume that it's coming from, background tissues. And this, moving all the way to the right, has to be blood flowing, right? So if you want to create a filter that's nice and sharp like that, can you do that with two samples? Like, obviously the answer is no, right? So what do you actually need? You actually need several samples along the tau direction. That's what you need. And that actually means that you have to fire your transducer. You have to transmit several times. That's it. That's it.
Teacher, how many samples will be enough?
That's a very good question. That is actually the question, right? And it doesn't have a very, very good answer, to be quite honest. I mean, of course, ideally, right? I mean, if you could have 100 firings of your transducer, that's probably great, right? I mean, you could design the best filters ever. what would be the drawback? Like if you actually have to fire, 100 times your transducer in order to analyze the data. What do you think obviously would be, one problem that you will run into?
It will take so many times.
It would take a really long time, right? I mean, your Doppler examination will probably be longer than an MRI scanner, right? And that's a problem, especially when you're looking again, you're trying to analyze things that are moving to begin with, right? And things like, again, like biological motion in general, because I mean, the person is like there and maybe you have breathing motion, but then I don't know, right? I mean, something itches and the person moves or something, and that's just not going to make it, right? So in practice, right? And also like there are so many other things that come into play, right? If we were to be looking at a phantom and we're just, pumping some, like blood mimicking fluid through a hole, then probably, yeah, you can argue that, I mean, we can actually, right, take maybe like a really long example of like 100 or maybe 1,000 transmits, but we know that that's not how the circulatory system works, right? Because your heart pumps blood in a pulsatile pattern, right? So it's not like your blood is flowing. Forget even about the fact that you have a profile because of, laminar flow and whatnot. It's not only that the blood is flowing over there, just doing whatever it is, but the speed is actually changing in time. And it's faster, and then it's slower, and it's faster again, and it's slower again, and it's faster again, and slower again, because your heart is pumping and it's pushing, and things go fast, and then it's contracting, so things are not moving as fast anymore, and then it pushes again, so on and so forth. So if you were to, again, have a super long ensemble, right, you wouldn't probably even be getting some meaningful blood flow estimates, because you would be looking at, parts where, the blood flow was supposed to be faster and then slower and then faster and slower, and you would completely lose the ability to identify that, because remember, you are looking into something that is not constant in time, right? The thing with dynamic imaging in general, when you're trying to look at things that are moving, is that you have to be able to create images not only fast enough that it's reasonable that you put them together, but you want to create them faster than, the typical rate of change of the variable that you're trying to measure. So you would not be able to just, put up with a super mega long ensemble, just because from a signal processing point of view, it makes it simpler for you, because, you would run into the inability to actually look at the flow that you're trying to characterize. That is an answer that probably doesn't satisfy your question, in the sense that, sure, great, I know they cannot be, and I understand why it cannot be mega long, but still, so how long can it be? How long can it be? It's still a tough question to answer. I can tell you that in practice, ultrasound systems that work with, like conventional imaging configurations, like based on focus beams and stuff, typically you will have ensemble sizes. Your ensemble is your collection of firings, right? So your ensemble size, meaning how many firings you have in your ensemble, would typically range in between, like 5 to maybe like 11 or 16. That's probably the highest that you would see, like 16 firings in an ensemble. Like 10, 11, 12 would probably be the ballpark of, the high number that most people would use, in the sense that it would be a good trade-off away from just having, 2, which nobody would use ever, and, getting into the high end of what you could reasonably do while preserving a good frame rate and being able to visualize the blood flow in the human cardiovascular system. So that would be, the long version of me saying up to 16, okay? But hopefully that clarifies the answer a little bit more.
Yeah, teacher, thank you.
Sure, no problem. That was a very good question. More questions? Okay, so let's go back to the slides. Slides. Okay, so for example, in here, right? This is an ensemble Doppler, like part of it, right? Part of the signal before doing any type of filtering. And you can see that, you know, there's a strong presence of stationary echoes. You see some variations in there because you can see that, you know, especially when you're going down towards the bottom, it's not like everything is a constant horizontally, right? But I mean, to a very large extent, it kind of looks like it. So you actually do the wall filtering and this is what you get. And by the way, even look at the way that the data looks, right? It's doing what you would assume that something, you know, coming from, you know, targets that are flowing at some speed would look like. The data, it looks like it's shifting, you know, up at a very slow rate. So it may be that, you know, you have your blood flow in a way that, you know, things are moving closer to the transducer, and that's what it would look like, and it's closer and closer and closer and closer and closer as time passes by. But this you can actually separate because, right? Because you're applying a filter. Otherwise, you wouldn't be able to see it at all. There are some more sophisticated ways, actually, of reducing the clutter. That's the name that this thing would have in the literature, right? Clutter, C-L-U-T-T-E-R. There are more sophisticated mechanisms to deal with it, like singular value decomposition-based methods, which are probably, you know, the king when you go to the literature on this. You also have empirical mode decomposition methods, which are, you know, data-driven algorithms that would allow you, in a sense, to, you know, decompose the data. So similar to wavelet transforms, maybe, in the sense that you can differentiate, you know, like in this case, it would be stationary from moving counterparts rather than, you know, high versus low frequencies. But when you really think about it, in the end, it's kind of the same thing, right? So there are several types of processing, you know, that go along the lines of what scanners would do in order to eliminate clutter. But the wall filter is the most basic one of them all. And it's one that, you know, nevertheless, and irrespectively of, you know, the type of processing that's done for reducing the clutter, you know, that's always going to be there, you know, as a very basic tool, you know, to get rid of these kind of things. So hopefully this helps, you know, clearing this out. So in general, right, I mean, the Kasai's algorithm, more than a disadvantage, it will have a trade-off in between, you know, spatial and temporal resolution and signal to noise ratio. As we mentioned before, right, I mean, the signal is very weak, it's going to be very noisy. So if you actually want to estimate something that's worth, you know, anything, then you also have to be averaging, like you have to do a lot of averaging, especially and in time also. The in time, we already saw it, right? That's built into Kasai's algorithm. You keep averaging, you know, like consecutive pulses, like 1 and 2, 2 and 3, 3 and 4, 4 and 5. You calculate, and start averaging and averaging and averaging. So that will reduce your temporal resolution in a sense, right? But it will improve the quality of your data. And you can also do that in spatial domain by averaging things from nearby locations, right? And you can have cleaner data. Like even in here, you know, you can see what it would look like if you were to start, you know, increasing the amount of averaging that you can have. But of course, in this particular, you know, set of data, the noise is almost non-existent. Like in practice, you know, you wouldn't be able to see anything. Literally, you won't be able to see anything if you were not to do some type of averaging. So one of these days, I should actually probably provide something that's coming, you know, from human data, so you can see how horrible the SNR can be. But the main disadvantage, because the other thing is not really a disadvantage, it's just, you know, I mean, that's just life. But a true disadvantage of Kasai's algorithm, right, and the phase derivative algorithm, or phase shift algorithm and whatnot, is one thing that we discussed on our last lecture, which is that the phase is periodic with period 2 pi So we actually run into a limitation of, how fast we can actually detect, the blood flow before we ram into our sampling frequency. And again, we have the Nyquist criterion, which basically tells us that we are not supposed to be looking at a frequency shift, right? Because we're kind of measuring that goes beyond how fast we're shooting the transducer, right? So it's the post-repetition frequency is the one that limits us, right? Because it kind of makes sense. I mean, we're looking into Doppler shifts, and we are not supposed to be looking at things, right, that go beyond the PRF. That wouldn't make any sense whatsoever. And that's where this really simple expression comes from, right? I mean, you can derive it from, any perspective you may want, right? But it's basically telling you that. And it's basically, I mean, the expression for the Doppler shift, right, with that factor of 2 adjusted, and we can actually, sorry for going back. I usually hate to go back. So you have your Doppler shift, right, which is Doppler shift is 2V cosine theta. So forget the cosine, right? So it would be 2V divided by C times F naught, right? So from a sampling point of view, what would be the maximum Doppler shift that you could obtain if you're sampling the data at a frequency of FPRF? What will be the maximum frequency that you can measure up that way? You know your Nyquist, right? So you can tell me what the answer is. If you're sampling something at FPRF, what's the maximum frequency that you can detect?
Half of it.
Half of it.
Correct. So that would be FPRF divided by 2, right? That would be the maximum, would be equal to 2 times the maximum velocity divided by C multiplied by F naught. Equivalently, that means that the maximum velocity would be equal to C times FPRF divided by 4 times F naught or something like that, right? Which is very likely the same thing that we have here. C divided by 4 times FPRF divided by F naught. Like, again, it's just, it's just what it is, right? There's no magic in there. That directly comes from there. Now, what does that mean in practice? Well, that's okay, right? I'll just increase my FPRF till the kingdom comes, right? And I'll make it 1 megahertz if I want to. And if I shoot the transducer super uber mega fast, things will be all right in the end. That sounds great, right? But there is one practical problem with that. Can you anticipate? I mean, it's actually elaborated in there, but does somebody actually care about elaborating why that is not feasible in practice?
Because we need to wait for an echo to go and come and return.
Correct. Because you're transmitting something, right? And then the signal is just doing its thing. And then eventually, right, it will like fade away because you have attenuating tissues, right? So the signal will make it up to a certain depth till it dies out, right? Like technically speaking, that depth is infinity, but it's not really like for it to completely vanish, right? But you have to wait it out, right? And then you can fire again. Because if you fire, your signal and then you fire 1 femtosecond after, then you're receiving echoes from the first transmission and you're, transmitting for a second time. So the signal that you're getting has information mixed from the 2 transmissions. Because you didn't give it time for the first set of echoes to disappear before you transmit the second time. So you have to wait, right? And if you assume that, there's a maximum depth at which your signal is going to make it alive, right? then you cannot have a PRF that is larger than, you know, the sound speed divided by 2 times that depth. Or work it out equivalently, it would be telling you that, you know, you have a certain depth, and the time of arrival of the echoes coming from that depth, right, cannot exceed the period of the PRF. That's basically what it's saying. You can actually combine these two, right? And figure out that if you want to, or equivalently speaking, right, I want to get signal from some particular depth, then I need the signal from that depth, you know, to like, signal goes and comes from that depth, comes to the transducer, then I fire it a second time. That's the fastest I could do if I want to get estimates from a given depth again. You can combine these two expressions very easily and derive an expression that will tell you, okay, fine. So if I want to obtain blood flow estimation from some target is located this many centimeters, and notice how everything in here is physics-based, right? It has nothing to do with anything else. The maximum speed that I could, you know, measure up for a given center frequency of my transducer is this much. You can directly estimate it, and it will tell you exactly, I mean, as a function of the depth that you want to analyze, the center frequency of the transducer, the sound speed. That's it, period. That's as fast as you could do it. And you will see that in practice, the PRF is limited to be in the kilohertz range. Like if you put in numbers, you know, that are typical of the things that you would do, you will see that it's in the kilohertz range. And that basically tells you, you know, that there will always be the potential for aliasing, because unfortunately, physics tells you that you cannot fire a transducer, you know, magically fast. Simply cannot, unfortunately. So in general, right, I mean, when you have like aliasing, for example, in here, you're going to see distorted profiles, right, that can actually get fixed if you increase the PRF, and again, you're not always going to be able to increase it. With Kasai's algorithm too, you know, if you have the gain not properly set up, so you have, you know, clipping of the signal because you're saturating your amplifiers, then that's going to distort or you know, prevent you from obtaining meaningful color flow maps. But you can fix it very easily too by just adjusting the gain properly. And there is just one thing that will take 2 minutes to wrap up, because, right, I mean, we're having our first invited lecture next week. So I'll probably want to wrap it up. Yeah, up to this slide only, which is, you know, just to wrap up with the difference in between the fixed window and the moving or variable window. It's a cross correlation algorithm. This is something that was studied very extensively back in the 1990s in the ultrasound community, okay? And it follows the intuition. I think one of you even said it, right? Like if I have 2 consecutive firings and I have, you know, one piece of signal that I want to see where it lands on the second one, I just cross correlate it, right? I just grab the thing and I keep sliding it on the second set of data until I find a location where I maximize the similarity, and I can do it by maximizing the correlation or some other, you know, similarity index. But the correlation was logically the one to go to. And to be quite honest, you know, you would probably have the same issues with any other similarity index that you would use. So in principle, this doesn't suffer from aliasing, right? Which is great. And it also has better signal to noise ratio, because rather than looking at, you know, just 2 samples, right? I mean, you're looking at the whole window. You can argue that you can have the same thing with Kasai's algorithm by averaging, you know, along several samples in the T domain. And it's true, right? But nevertheless, the issue actually came with something else. And the issue came with the fact that in practice, these algorithms simply just didn't work. Look at the signal at the bottom of this slide, which is some correlation, you know, in the fast domain. And you will see that, yes, there is a peak, right? But there are also several other peaks, right? And in practice, what people found out was that this is actually, you know, a cartoon, and it's a cartoon from a very lovely autocorrelation function. In practice, autocorrelation functions had a lot of peaks that were very, very similar in amplitude. Remember what we said, you know, when we were motivating Doppler, and again, I'm sorry, I'm just going to go back a lot. And I said, look at these two, right? Look at these two signals. And this is what decorrelation will do to you. The signal is not exactly identical, you know, from one firing to the other. So you can easily imagine, sorry again for going back, you can easily imagine that if this autocorrelation function looks that crappy, you know, for such a perfect signal, the minute that you have the correlation, you can easily have one of those, you know, this is not a true peak, but it kind of looks like it peaks, actually overcome the location of the true shift very easily. So you don't have aliasing, but you have a probability of false detection. And in practice, that was actually worse. Aliasing you could live with, you could predict it, you know, and in practice, you know, it's like realistically speaking, because we understand, you know, the amounts of like the numbers that we would expect, you know, for reasonable blood flows, then you could even understand that you had aliasing in front of you. But the probability of false detection was too unreliable. Because, I mean, you could randomly be having, you know, something that looks like something that's very far away. So that would mean that you have a very, very high flow speed, or indiscriminately close, which would tell you that you have a very, very low flow speed. And those things would occur, you know, not completely at random. You will have control over it, right? You could say, move at the most, you know, this many seconds to the left and right. You know, you can control it with some parameters, but it was still very unreliable. And the other issue was that it had a very high computational cost. And you have to understand, you know, the challenge always is to, especially for ultrasound, is to create images in real time. So the thing was, this was an algorithm that was actually way more expensive, because it was way more expensive than Kasai's algorithm from a computational point of view. And that would have been okay, had it been that there were really not real advantages, because it would still give you, you know, images that would suffer from distortions. And actually these distortions could be even worse than the ones that were provided by Kasai's algorithm. So in an ideal world, this would have been perfect, but in the real world, it just doesn't work at all. Okay, and this hopefully also, you know, comes to show you that many times when you do research, you may start from a very reasonable hypothesis, and you can do science that, you know, people would think this is very reasonable to do, and you will come to a solution that is, well, guess what? This is just pointless, right? Because really, I mean, this doesn't work at all, and that is okay. Because if people haven't done those kind of studies back in the 90s, and there were tons of people doing it, then we wouldn't know that this just doesn't work. Yeah. So sometimes somebody has to do those things, you know, for you, and that's okay. Sometimes, someday, maybe you will do something like this too. A negative result is not a bad result. It's just, you know, a different piece of knowledge. Just never forget that. Questions up to this point, so we can wrap up today's lecture? Okay, so if we don't have any follow, yes.
Yeah, but well, this is not about the material, but actually, I was going to ask you for you to upload the last class.
Oh, the last lecture is not uploaded. Thank you. I will upload it ASAP. Okay.
Yes, and the other question is that at the end of the lecture on Thursday, will we have a quiz too?
That is a very good question. We actually have our invited lecture this Thursday. So I think for the time being, for this particular week, we're probably not going to have a quiz.
Okay, teacher.
That's a good question.
Thanks, teacher.
which again motivates the fact that,
Perfecto.
remember,
Yeah.
Mujinatu is giving her lecture this upcoming 30th at 4 p.m. So be there, enjoy it, and come prepared with tons of questions for her.
Teacher, excuse me.
Yes.
When are we going to have the answers about the topic that we sent on Saturday, I think?
So typically what I do is I take some time during the week to look at this. So I mean, so you're talking about the proposals for the project, and some of you may have been filling out the form already.
Yes, exactly.
Right. So I mean, at some point this week, for sure, you will have feedback coming from me.
All right. Thank you very much.
Sure, no problem. Okay, guys, thank you, and I'll see you on Thursday.
See you, teacher.
Bye.
Teacher.
Take care.